Hi, Wim Dijkgraaf here, Metal Heaven. Here a tutorial that gives you some insight about the fundamental architecture on which Rhodium-24 is based. This is critical to understand because it gives insight in the potential in the future of where we can get with rhodium, especially for those factories who are multi-factories, think in terms of digital twins and a virtual factory in the cloud, and want the ability to estimate across factories and resources, etc. So I'm going to give you some insight here, what we can do in the nearby future because of the basis of our architecture. Let's switch to this screen. And before I do that, before I show you some things in Rhodium itself, I play a small video by Microsoft about Microsoft Orleans and especially how they applied it in the popular game Halo. So everything that you see here is actually the way Rhodium is built upon. So there we go.
Halo is a rich, immersive story with millions of loyal and dedicated fans. We deliver an exciting and engaging experience to these fans. They need to know what the hot playlist is today. They need to know what the challenges are. They need to know where their friends have been, what their friends have been playing. Have their friends gotten more medals than them? They need to know all of this, and they need to react to it and interact with their friends in real time. We need to deliver hundreds of thousands of updates per second to millions of players across the Halo universe. We need to get them the right information to the right device at the right time. There was nothing off the shelf that solved the problems we needed to solve at the scale we needed to solve them. So we turned to Microsoft's Extreme Computing Group.
Hundreds of thousands of requests per second across thousands of servers in real time. These guys are crazy. But in extreme computing, those are the kind of challenges we like to tackle.
For us, using Windows Azure was a no-brainer. Platform as a service allows us to get thousands of nodes, abstracting away the operating system without having to worry about a thing. We're able to use storage to store massive amounts of data, and we can use Service Bus to route hundreds of thousands of messages around the system without a problem. Now, we need a programming model that allows us to scale limitlessly, transcending the machine boundaries while still maintaining that real-time performance need that we have.
We took the actor model approach and we built a modern cloud-scale distributed framework optimized for Windows Azure. We call it Orleans, and that's the framework that allows us to build large graphs of live actors distributed across thousands of machines, and those actors can interact in real time. In our lab, we tested one of the real services, handling over 1 million requests per second on just 125 servers.
So Microsoft Orleans is what the kernel of Rhodium is also based on, same as the game Halo. To give you some insight here, I have an Orleans dashboard connected to the production environment. There are a couple of menus here. You are not able to see that. It's our monitoring, one of our monitoring systems. And what you see here is that 5 silos are active. So the terminology here is silos. Within silos live grains. And grains are similar to virtual twins or actors. So we see 5 silos, and grains are living across the cluster inside of those silos. And here we see some examples of grains. Let me order this by alphabetical order. So for example, our Rhodium agent is a grain. Those managers that manage articles and their prices are grains. Parties are grains, so all the factories are grains. Resources are grains, so the machines inside of those factories are grains. And we have a whole workflow engine distributed across the cluster with workflow step grains. Okay, so let's focus on activations and let's see what happens if we start uploading some geometries to step files here. And what you will notice is that the amount of activations across the cluster will increase. There it goes. And we see workflow step grains, 17, 24. The amount of activations increase because the assembly is disassembled. For every part we create step files, the thumbnails, we do feature analysis, we do volume and area analysis, etc., etc. That is done over the cluster of machines, and you see as those workflow steps are finished, the workflow step grains are deactivated, and yeah, that's now the workflow is performed. So if we go back here, then everything is has been processed. Now I can upload a bill of materials Excel, which assigns material to all of these parts, which will trigger the whole estimation engine. And then we will see that the estimators become active. You see 63 estimators here. So for every activity, every geometry, there is an estimator active now, independent for which factory that estimator works. So the whole platform can be filled with hundreds of active estimators working together to estimate a specific calculation or project. So probably now we will see some values here, and of course the whole nesting, etc. here. So this shows the distributed nature of Rhodium. Distributed meaning multiple machines in a cluster. It's a Kubernetes cluster. That's technology to host Docker containers, and those silos live within those containers, can be distributed across the cluster in various data centers around the world. So in that sense, the capacity that we can handle is virtually limitless. And so I hope this gives you an overview or some insight in how we approach this whole problem of multi-factory organizations, digital twins, communicating with agents, doing estimations, etc. in a distributed cloud environment. So it's really a cloud-native application. I hope this gave you some insight, and see you in a next tutorial. Thank you.